Let me just drop this. Okay.
Okay, so hi everyone. Thanks for making it here today. I hope you're not soaked in the rain. I'm Yichen, one of the speaker liaisons at COPS this year. And then today, I'm honored to introduce Dr. Nur Ünal, a theoretical physicist who just recently moved from the theory of condensed matter group here at Cambridge to the University of Birmingham. Congrats. And then she's now an assistant professor in Royal Society University Research Fellow there. Previously at Cambridge, she held a Marie Curie and Royal Society Newton Fellowship and has taught TP2 in past years. Before then, she also worked as a postdoc at the Max Planck Institute in Dresden, Germany, and as a visiting scientist at Cornell University. So before further ado, I'll hand over to Dr. Nur for a talk about quantum simulation and ultracold quantum gases. Okay.
Thank you. Thank you. That's very kind of you. It's nice to see you here. I'm soaked. Yeah, thank you for the introduction and invitation. So I put things a little bit from everything. Okay. So and then I would be happy if you interrupt me at any point. We can go as it go. I don't have to finish all my slides. And so I will be talking about quantum simulations, topology, quantum geometry, if it comes to it. And so I will start with like ultracold atoms are like one way of doing quantum simulations. So these are analog quantum computers. So I will first give you an introduction to that, then go to topology, what is topology, and which comes from the quantum geometry. So that's kind of the outline of the talk. So let me directly start. So what we are trying to do here is that, like, as in physics, we want to know how things work, right? So like to understand the laws of nature, and then once we do that, we know quantum mechanics, we know electromagnetic theory, so we can design new quantum materials. So it's something that's really like connected to the experiments, right? Although I do pure theory, for example. And then this translates to technological applications. We can just like predict new things, right? And this is the ultimate goal, but there's a big but. And that is that, like, most of the time, we know the underlying rules, how things work, okay? But even though we know them, that solving those equations are something entirely different. So that's something that, like, you will be seeing in TP2, for example, right? And then we cannot solve the problems, so it's mostly too complicated. And and most of the time, sometimes we don't know what the rules are, what the equations governing those things are. And then when you're dealing with something too complex, your instinct is to divide and conquer, right? Like try to just like control whatever complexity that's arising. And that's something that's hard to do, okay? So this is a huge problem. And then it comes from the many-body nature of the quantum mechanics. So if you are in a classical world, okay? So you have like solving the computation problem, okay? So because there's this equation, huge equation that you don't know how to solve. So I can make use of my computer here. And then the way that like this works is that like classically you have 1, 0 qubits. That's how you're just like processing information, right? If you have one spin, it can be up and down. So this is how you store information. So when you go quantum, the problem is that, and then that's why the beauty of it is that there is something called superposition. So if I have some spin system here, okay, so when classically the information I store is up, down, whatever configuration that is, and then if I have big enough memory, I can just like put it there and then do any calculation with it. Here, quantum mechanically, if I have n spins, so they can be in the wave function, the state of the system can be in a simultaneous superposition of all those things, right? In the spirit of the Schrödinger's cat. So to store this information of this quantum mechanical state, I need C to like 2 to power n complex numbers. And complex numbers more than already, it requires more than real number, right? So I need all these complex numbers just to store this information. And this is something that the complexity of problem grows exponentially. Adding one more spin to the system, it already doubles the space that like I need to memory that I need to access, right? And then like, so the large number of particles become untractable pretty quickly. And then with large numbers, I don't mean something like, oh, million atoms or whatever. I just like mean 250, for example, spins. If I want to, if you just like write down all these superpositions, combinations, so you need 2 to power n of these complex numbers, okay? So this is already out of question, like classically storing that information. And this is something known as Eddington number. So that's why I picked this number. It's a 250 something or 267 or whatever that is. So our beloved Sir Arthur Eddington, when he was giving a lecture in Trinity College, so this number, 2 to power n, for this large n, it's known as Eddington number. And then he just like says that like he calculated the number of protons in the entire universe. So that's what Eddington number is. And then this number, I'm not going to try to read it. So that's, it also has its own like funny story that like he was trying to predict that the fine structure constant. And then after a few years ago, he changes his proof that like he's trying to say that like there is this number of protons in the universe, just like gives that thing. So which is something like today we don't believe that there's a connection between them. But the point here is that like even if you want to simulate some 250 spins just to store the information, you need to use all the protons, like estimated number, huge approximations or whatever, but it's a huge number. Okay, so you cannot store that information, let alone just like do any calculation. So this is something very hard. What can we do? Any suggestions? Anything? When there's something really hard problem that like we cannot do, there's something we, as physicists, I don't know whether we are all physicists actually, but as physicists, we are really good at approximating. Right? So you're just like good at approximating cows as spherical objects. So we do approximations, and there are really good approximations, just like when we are trying to just like access this huge Hilbert space information. So there are like techniques called like DMRG, you know, Monte Carlo simulation. So we can treat really large many numbers. But problem with these approximations is these methods is that usually they work either at ground state or really restricted phenomena or just like giving some one-dimensional problems. So they are really powerful, but they are very restricted, okay? So that is one way of going around it. And it's a really powerful way that like we are applying day to day, okay? Another way, another just like proposal comes from Feynman. So the problem arises because the objects that I'm trying to simulate that I put there, they are quantum, right? Those quantum, so they can be in a superposition. So if I employ something quantum, some like quantum objects to do the calculation for me. So the problem is that like I'm trying to employ something classical to do the quantum computation here. But if I use atoms, for example, that are already like following the quantum mechanics rules, so that is what quantum simulations is, using a simpler, more controllable system to solve something really big that's something untractable. So the idea is that there is this really interesting thing that like we want to, where's my pointer? Oh yeah, here. So there's this interesting physics, superconductivity. I want to understand high temperature superconductivity, magnetism, ferromagnetism, okay? So I need to just like know a lot of particles and then they are interacting and then there's this emergent phenomena coming out of it. So what I can do is that like I can just like write down this Hamiltonian as some kinetic interaction, like whatever, just like confinement term, whatever. And then if I can create this Hamiltonian artificially in the lab in a controllable way. And then on the other side, if I prepare some collection of atoms that are at their quantum mechanical state, and then apply that Hamiltonian on these atoms, So the atoms know the rules. They just like follow the quantum mechanics rules. So they are going to evolve, do whatever response they are going to give under this Hamiltonian that I want to solve. So they are doing the calculation. And then if I measure their energy at the end, I will get clues for the original physics that I was trying to get the information. Okay? And then I take that, feed it into the original assumption, just like development. So that is the gist of quantum simulations. And then when Feynman suggested this thing decades ago, and then that idea picked up very quickly. So ultracold atoms are just like one really just like huge field that's been like where this idea has been applied successfully. So what's happening is that at room temperatures, at really high temperatures, so I have all these atoms just like scattering around everywhere, right? Just like this temperature is kind of the dominating scale. Like I cannot get the quantum information out of it. But by using really sophisticated cooling techniques like laser cooling, for example, if you just like shoot these atoms in the labs out of an oven, they are extremely hot, okay? So rubidium atoms, sodium atoms. And then if you shine some laser light head on, like in the opposite direction, so these are just like absorbing that atom, but then they are going to emit in all directions randomly. So they will end up decreasing their momentum, very slowing down, something called laser cooling. And then you can put traps to these atoms, trap these atoms with some like harmonic oscillator potentials. And then the hot atoms are going to be closer to the edge of your trap. If you just like open your trap up slowly, so the hot atoms will escape. So whatever is remaining here will be much colder. So by using several cooling techniques, so these atoms from the room temperatures can be cooled down to the nanokelvins. And then these, like inside the cold atom, like the vacuum chambers in cold atom labs, so those are the coldest places in the universe. We're talking about nanokelvin temperatures as opposed to 3 Kelvin, whatever, at this space. So they are extremely cold. And what's happening when they are really cold is that at high temperatures, so the interparticle distance is just like correlates to the density, right? Roughly, inverse density. And then the more that like you cool them, all these atoms, so they have their inside de Broglie wavelength, which is controlled by the temperature. Here. The more you cool them, their wave nature becomes more pronounced, okay? You keep cooling, and then there can be other energy scales. So here AS is something called scattering, which is something that like you would see in TP2, or you have seen if you're already taking that course. So interaction scales, whatever. So if you just like really cool them, these waves start overlapping. And then all atoms combined, they behave like a giant quantum mechanical wave. And that is the state that we are trying to go. So that is the atoms that like we want to prepare to apply any Hamiltonian we want to solve eventually. So at room temperatures, so this is like a classical particle behavior, right? They're just like scattering around, temperature is dominating. And then the more that like we cool them, we just like have the coherent quantum mechanical like wave-like nature getting amplified. And so this is something you can also understand from the point of view of Heisenberg principle, for example. So like as you're just like cooling these atoms, the uncertainty in momentum deviation is just like decreasing, right? So delta X must be really large. So your atoms, if you just like look at them, they are really fuzzy. At high temperatures, they are well-defined objects, like atoms, but then the more that like you cool them, delta X is really large. So they are really fuzzy, they are overlapping, and then they are forming this giant wave. Here, that is a picture of a famous like Bose-Einstein condensation, all atoms, yes? Yes. Yes, so like this like there are different scales, like what you are looking at, depending on the physics as you want. But yes, these really behave like a giant single wave that you do. So for example, here, just like in these Bose-Einstein condensers, so there are several quantum like levels. For example, these are bosons. Imagine a harmonic oscillator. So there are several different layers, right? All your bosons are just like occupying the single, the ground state. Most of them. There's something called condensate fraction. So most of them, like 99% of them, they're just like following it and then for forming that. Exactly. So that is what we are trying to get. Okay, so once these objects are really, really, really quantum, so then practically what we are doing, what we are trying to do is in principle that, so they are very small, they're really dilute, but if the physics that I'm trying to access, for example, here, this is graphite, and then at the macroscopic scales, at the nanoscales, angstrom scales, there is structure to it, right? But it's usually really packed that we cannot see. For example, if I can, in the experiment, in the labs, if I can just like expand this structure 10,000-fold, I would actually see that, oh, there are actually honeycomb patterns, like graphene sheets, like stack on top of each other. But seeing this thing, looking at this thing, like with any equipment, with just like optical systems that like we have, that's extremely hard. But if I can make things much larger, I can use my normal like microscopes or whatever optical techniques that I have to do it. So that's in a sense what's happening when we apply these Hamiltonians. So, and that's enlarging this length scales. So that's the way that like that works is that in a real system, if you have like graphene, how this lattice, for example, is formed is that like there are ions, right? They're just like sitting at some pattern. And then these electrons are just like feeling that potential. So they are just like arranging themselves, whatever, depending on whatever the chemical structure there, right? So that is what a real lattice is. But now I want to create the same structure artificially. What I can do is that like I can just like send some laser light, put a mirror, reflect it onto itself. So these laser lights is going to form some standing wave, right? And then if I just like put some atoms, so not electrons, so those were just like the electric charge. Here, those white dots there, they are full-blown atoms. So they are much larger. They're rubidium-87 atoms, potassium-40 atoms. So if I just like put these atoms in that laser potential that they are gonna go and then sit at the potential minimas, or just debated like they interact at the maximas, okay? So then they arrange themselves in this lattice structure that I created there. And that's something I can control. Like if I just like send two laser lights at 90 degrees, they're going to interfere and then form a square lattice pattern, right? If I can also confine them along the z direction, for example. If I send them at 120 degrees, I can create a honeycomb pattern there. So I can create this Hamiltonian, the physics that like I'm after, some real lattice, artificially create the potential by using lattice, but it's going to be much larger scale. I can control the scale. I can control their interaction. So by using these techniques, you can create like pancakes, for example, if you apply some confinement potential along this direction. And then if this potential is very like, you're just like sending some laser light and then it's very deep. Okay, so your atoms are going to feel like pancakes from there. If you just like put more lasers, you can just like create cigar-shaped traps. You can create square lattices. Yes. Yes. So that is the limit that we can do. So as I said, like, so these atoms that like I sent, so if the potential that I drove there, so that's literally the intensity of the laser. So if it is very deep, so that red potential is going to be very deep. So your atoms are going to go sit at the minimas, and there's a huge potential barrier, so they cannot hop. So that's frozen dynamics. That's not that interesting, maybe. But if my laser potential, if the power is very small, then it's going to be very shallow. Then your atoms may or may not feel anything. But this is a physics that like mods to superfluid transition, for example, you can choose. So what we are doing here is exactly tight binding limit, but you can go there slowly and then control, like, because if your lattice potential is not too deep, your atoms can hop, but they can also hop to the next nearest neighbors. So you can control like what level that, like what orbitals that like you're accessing. So that actually, that's a really nice question. So you can control the connectivity of the lattice in that way. So these are just like some like two-dimensional patterns, Kagome lattice. You can go a little bit more, and then you can create quasicrystals. So this is a picture from Cavendish, Uli Schneider's group, for example. It's an 8-fold symmetric quasicrystal. So in 2D, you can tile the plane with square place. So there are certain symmetries that are allowed. But 8-fold symmetry is not allowed. You cannot find an 8-fold fully periodic lattice. So 5-fold, 10-fold are forbidden. So these are quasicrystals. So and naturally, in nature, they appear only in really extreme conditions. So like in meteorites, extremely huge pressure, under huge pressure. But if you have 4 laser lights, as I said, and if you arrange them at 45 degrees and then interfere them, so you can create this 8-fold symmetric lattice pattern and then see actually the quasicrystal pattern. Okay, so and then there are like in recent year there are also techniques that are developing called quantum gas microscopes. So where the microscope name comes from is that like technological. So these advances feed into technological, just like applications, but then it's also the other way around. The better cameras that like you have with better numerical aperture, so they can control at the lattice level the individual potential. So they can put whatever the mask they want on the lattice. So that's something what quantum gas microscope, because you're just like really individually controlling atoms. Or their optical tweezers are, again, another recent thing. So then these tweezers just like they catch the atoms individually, and then you can just like make them, drop them, whatever they are. You can just like draw any shape. So that's from Paris group, and then they're French. They're drawing Eiffel Tower, of course. So you have connectivity. So and then this potential that like you're engineering here, for example, that goes to the kinetic energy part of your Hamiltonian, right? But then so these atoms, like as I said, so I'm simulating electrons, but I told you like these atoms are neutral atoms, right? So they cannot couple to magnetic fields, for example. So their interactions are just a Coulomb interaction is very weak. So they don't interact via Coulomb interactions. They interact something called the Feshbach resonance. So by tuning external magnetic fields, they can control how atoms interact through contact interactions. So, or you can, if they are like dipolar gases, so they can interact with dipolar interactions. So interactions are something very controllable. Okay, so you can make them interact very weakly, very strongly attract, extremely strongly repel. So through the full range you can do, and then that capability is something that allowed to observe something called BEC to BCS crossover. They cross the whole regime, for example. Just trying to highlight the capabilities here. So, and then another thing is that like you can control the external confining potential. So you can put artificial electric fields, artificial magnetic fields. You can create a dimension of whatever physics you do. You can go to higher dimensions. 4-dimensional experiments are done. 60s or something. You can just like create systems that are like immediately beyond what we have, and then learn something there. Employ those dimensions so hyperbolic geometries are something, another thing. So it connects to ADS-CFT correspondence, for example, in condensed matter. So there's a huge capability here. Okay, so we have this thing, and then the way that like the physics we are trying to address is that like, I mean, condensed matter is what I'm going to give you an example. So I am a condensed matter theorist. And there are several different systems, so like MV centers, superconducting qubits, cold atoms, photons, photonic lattices. So there are several different mediums to do this, apply this Feynman's idea. And then physics you can do is that you can simulate black holes. So you can simulate lattice gauge theories. You can simulate topological insulators. So and the point here is that they are really good for proof of principle studies, like if you want to understand what's happening. And then we can develop new probes, but then we can also go to regimes that are like beyond the immediate, like again, like 6-dimensional quantum Hall physics, for example, something you can imagine and probe. So that's what I will be doing, is that like condensed matter, atoms and topology. So like I will just like show you some examples there, okay? And then what I do in my day-to-day research is that I will tell you about topology in a minute. And so topology is something that's been attracting a lot of attention in physics in recent decades. So what I do is that like there are these topological systems. If we go to out of equilibrium settings, under some periodic driving, under some laser lights, or just like quantum quenches. So there are new topologies, new regimes that they are arising. And then there's a lot of things that like we can learn, apply from there. So that's what I'm doing in my day-to-day research. And I will show you 3 examples. Like one, something called linking number, how topological singularities in the wave functions can form links. And that's something that can be experimentally observed. So that's some topological number. That's some, I think is pretty cool. And then there are things called like braiding, non-Abelian braiding, which connects to fractional quantum Hall effect, quantum computation applications, whatever. I've come from the more like fundamental literature. So there are things called like there are bosons, fermions, and anyons are in between. They have fractional statistics. You can braid them in 2D, and then entirely new physics come up. So I will show you a single example, not with in band topology, and then yes, some out of equilibrium example. So now let's start. So what's topology? So how topology entered our lives in physics is with this experiment from Klaus von Klitzing. He took a 2-dimensional electron gas, cooled it not to nanokelvins, but cold enough temperature under a magnetic field. So if you have a magnetic field through the plane here, so your electrons will form those cyclotron orbits, right? And then at the edge, because this magnetic field is just like Lorentz force is choosing a direction for your currents, right? So because of this magnetic field, so electrons just like go through the edges, and then classically this is something known as a Hall effect. But in this experiment, in cold enough temperatures, if you do it, quantum Hall effect happens, and then the quantumness comes from those steps there. So if you just like apply some voltage and then measure the transverse conductivity along there, the conductivity with as a strength, as a function of the magnetic field, it doesn't increase linearly, it goes as jumps. And this is something extremely robust. Like if you change your magnetic field here, so this axis is the magnetic field, your conductivity remains same. So you can put some impurities to your system. You can increase the temperature, but you have a really stable conductivity value that is fixed at E over H, something. And then only after really some like big changes, it jumps. And that's something too big. Like it just like creates a lot of like attention at that time, and then the connection to underlying topology, like Chern numbers, it just like comes afterwards. And this is something just like let me just like give you a remark. So that ratio there, E over H, is so precise. And this is how, like a couple of years ago, just like National Standards Institute actually changed, like how we define the natural constant. So it is extremely robust that you can do. It stays there. You can measure really E over H very precisely. Why that thing is very precise is connects to mathematical idea of topology, that like I can do some changes to my system, and then those changes are gonna just like remain there. It doesn't change. So number of holes in a chocolate ball, donuts, and a pretzel are different. Number of holes are the key quantum things here. And then those number of holes define which plateau you're going to be on. Okay? And how, if I just like go back a little bit, these ideas goes back to Euler's time. And this is a picture of Königsberg. So at that time, the question was that that's the river, and then the bridges are marked as red. And the question is that like starting from somewhere, can you design a road that crosses all the bridges, but also only once? So you want to cross some. And that's a topological question that Euler answered, for example. How it comes to our lives in condensed matter, to understand that, we need to start with something called band topology. When I have a lattice, so the particles that are there, so they have like the quantum mechanical waves, right? And because of the lattice periodic potential, so those waves can diffract. They feel the lattice structure. And then instead of, if I have a free electron, I have this continuous dispersion, right? They can be at any energy here. But when these waves feel the lattice, something called energy bands appear. So some energies are those gaps, they are forbidden. Okay, so my particles cannot have that energy. To have that physics, I need to have, so this is something called the Bloch theorem. And when I have those gaps to access this physics, I need minimum 2 bands, so 1 gap here. Okay, so this is a 2-level function, and then Hamiltonian is given by some metrics. Here I'm jumping a little bit to give you a little bit of, like, if you don't know what quasi-momentum or Bloch theory is, you can just like take my word that there is this energy bands, okay? At each momenta, there is a wave function. And then the point is that the collection of these wave functions in a band, they are going to form a structure in their Hilbert space. That structure is going to have certain number of holes in it, and that number is quantized. And that number dictates what your hole conductivity is. And that's something we can precisely calculate very well. How this is happening is that, like, if I take one of those bands, for example, I'm just like taking one of the eigenstates of this Hamiltonian as a function of all these momenta, HK. So that's just a two-level wave function, okay? It can be represented as a state on the Bloch sphere, which means that in 2-level systems, so they are represented by Pauli matrices, they span SU2 algebra, they point to some direction. This is like a spin system, okay? If I start from a trivial system, so this momentum space is periodic, okay? So it actually lives on a torus. So this edge is identified with that edge, so it's closed. That edge is identified with that edge. It's also closed that direction. So it's identical to a torus, okay? So at each momenta, at this state, I have some wave function. I'm just like solving that Hamiltonian, okay? And it points to some direction on the Bloch sphere. So if I'm in a trivial state, all these things are gonna point to some same point. I can do some changes to my system. For example, I can apply electric field, put disorder, increase my magnetic field. So they are going to spread a little bit. But because this is a closed surface, so is there a paper there? No, there's no paper. Okay, I can. This is a napkin. So this is a Brillouin zone. Imagine that this is a torus, which means that like these edges are actually closed. And those edges are also actually closed, okay? So at each point, I have some wave function. I have some function. It points to some direction. And then I want you to map this wave function to a sphere. So this must be, if you're trying to put this surface collection of wave functions on a sphere, it cannot be an open surface, okay? Mathematically, this must be a closed surface. So which means that like on this sphere, it looks like a deflated balloon, actually. The opening is tied up. So it's just like covers somewhere. But at the edge of it, if I just like keep going, it actually continues here, right? So it cannot be an open surface on the sphere. So that's why it's like a deflated balloon. It's just like going, covering some area on the sphere, but it comes back and then closes into itself. So there are 2 layers of it, okay? So when I make some changes to my system, in the physical system, increase the magnetic field, increase temperature, so that distribution is changing. It could be covering all the way to the sphere. I also have it here. But then it should come back and close to itself. I need to, the change that I'm doing to the system, it must be something, I have a faulty picture. So it must be something so drastic to my balloon from that stage to that stage. I need to punch a hole and reconnect it to the bottom, okay? And that punching a hole happens through a band touching point. So I had two band structures, right? So this was solutions of the eigenstates. If at any point, if they touch, if there's a degeneracy in the Hamiltonian, you cannot find eigenstates reliably there, any combination. So what I'm doing is that like I'm looking at the collection of the wave functions. They have a well-defined map, but from here to here, if there is at that band touching point, there is no map to the sphere. I cannot plot that point, okay? And then once they are open again, then I can point, but then the topological number change. So those are kind of the artificial holes. And then when you are first hearing about this thing, it might be so alien. So this was something that like I noticed when I was teaching TP2, for example, that that like the idea of Berry phase, it's a little bit abstract, like perturbation theory we know, right? Like you can just like take the derivatives and then apply that thing. But the more just like you just like think about, play with these equations, and then mathematically we can just like write them very precisely, you start thinking about these geometric pictures much more intuitively. Do you have a question? You look like you have a question. Yes, yes. Yes, exactly, exactly. Yes, so it does work. It does work. So that's why like the techniques that we know from the field theory or just like from math, we can just like take and then apply here. And then these singularities, for example, so they have some topological charges. We can study them. The experimentalists can even measure them. So they apply. Okay. So what we need to do is that we need to just like usually consider here in this context is that like this is a physical system. Because it's a physical system, there are certain constraints coming from those things. And then they actually, what we are applying those constraints, and then same thing. The equations are same in a sense. So, and if you're interested in, so this is actually what we have when we have a Chern number one hole. So this is actually what's a magnetic monopole is in a momentum space. And then the Dirac's idea, there's a magnetic monopole, there's a Dirac string attached to it. So this is naturally realized in momentum space, okay? So just giving for reference. So that is the topology introduction. Okay, a little bit. So, and Chern number is in a way the simplest or like first example that appeared. And when we go out of equilibrium, something interesting and crazy happens. And that's my first example I want to flash. I'm not going to go into too much details. So imagine that you have this two-dimensional system, some lattice, and then you start from a topologically trivial regime. So Chern number is 0. Nothing is interesting in that sense, okay? And then the Hamiltonian, this system was artificially designed, right? Like I created this Hamiltonian artificially. I can suddenly change the Hamiltonian if I have an optical lattice, for example, because those were created by some laser potentials. I can suddenly turn them on, turn them off, okay? And this quantum quenches is some capability that are brought from that way, for example. I suddenly change it, so wave function will start evolving. It's not in the ground state right now. When I started, it's going to start evolving. And then while it's evolving, there can be topological singularities in the wave functions. The points that like something in the wave function is not defined. For example, here the azimuthal angle is ill-defined, whatever. And then this is experimental data from my collaborators. So as the wave function is evolving, so these singularities appear, and then they can be tracked. Okay, and then they form links. Okay, so the red ones and blue ones, there are two kinds of singularities. One of them has positive charges, the other one has negative charges, whatever. So it links like that. Okay, the up and bottom ends of these oranges are also close, so they link. Okay, and then you can do some changes. So this link is going to be deformed. Okay, but to undo the link, you need to do something drastic, really change it, and that is the topological robustness here. And here, this is the link. If your Chern number, if you're quenching between topologically different Hamiltonians, you see a link. If they're 0, if they're the same, you don't see a link. And that's something a little bit like the counting the holes on donuts or pretzels. So a little bit just like really just like you're doing the calculation. And this is something mathematically known as linking number. And again, just to maybe, if I can convince you that like, oh, these are interesting. So mathematically, to see a linking number, we use something called a hope map. I'm not going to go into details, okay? But so these are, you all know complex numbers, okay? So complex numbers are like when I have a real number, complex numbers lives on R2, right? I have two real numbers to define it. So quaternions extend onto complex numbers. So they have one real index, x0, and then three imaginary axes, ijk. So ijk are all imaginary numbers. And they are actually the rotation, like three-dimensional rotation matrix, as we know it, that like you can write it by heart. Quaternions are generators of the rotations in 3D. So you can write that, obtain that same rotation matrix by using quaternions. And then this is a really nice quote from John Baez that I like. So there are four non-division algebras, exactly, and then mathematicians can show that there are no more. So the real numbers are the dependable breadwinner of the family, the complete ordered field we all rely on. The complex numbers are the slightly flashier, but still respectable younger brother, not ordered, but algebraically complete. Quaternions, being non-commutative, so rotations in 3D are non-commutative, right? Rotating along axis. So that's because of that. So they are the eccentric cousin who is shunned at important family gatherings. And then there's one more, octonions. They're the crazy old uncle that we are not taking out of. So to understand those linkings, that like those topological singularities, they just like move around and form that link twice are here. So that's an algebra that like we are employing on day-to-day, for example. And so they are discovered by Hamilton, by the way. If you go to Dublin, go to the bridge, the leg of the bridge. The IJK quaternions are prescribed there, so you can see that. Okay. So and this is the rotation matrix written by like some vector angle rotated around it, and that's by quaternions. I'm not going into there. And this is the linking, a broken slide. So that's how we are seeing to do this thing. So what we have is that we started with a two-dimensional system. I had kx, ky that lived on a two torus. When I quench it, time evolution also comes back to itself at some point. So that brings one more periodicity. That's something I can connect to three torus, which I can connect to three sphere. At each point, it lives on two sphere, and then that's how these hope linking number appears. So that's something that that's something very abstract mathematically, right? I'm just like telling you that like imagine a three sphere that lives in a four-dimensional space, and map every point on that three sphere to a two sphere, which is the normal sphere that as you know it. There is some linking number that controls this map. So that's something very abstract mathematical topology, okay? But that's something that appears directly in the evolution of the wave function, okay? So that is one example, okay? When you go to out of equilibrium, there are like new invariants, linking numbers that appear and can be experimentally measured. So this is another way of that, like you can go out of equilibrium. For example, we started with a two-dimensional electron gas in 1982, right? If I take that two-dimensional electron gas, all right, if I take this graphene sheet, for example, and if I send some laser light on it, so this laser is constantly pumping energy to this system. So energy is not conserved anymore, right? I cannot talk about energy. So that's something that's described by a Floquet theorem, Floquet-Bloch theorem. So what happens, so originally I introduced a lattice, right? So a lattice compared to free uniform system, which has continuous translational symmetry, a lattice has discrete translational symmetry. So in continuum, I have momentum. In lattice, I have quasi-momentum because I broke some symmetry from continuous translations to time translation. So now, if I have a time-independent system, I have continuous time translations. And the reciprocal energy is well conserved, well defined, right? If I break the continuous time translations to discrete time translations, because now I have a laser, for example, right? The laser periodicity makes Hamiltonian periodic with the periodic of the Hamiltonian. So instead of energy, I can define quasi-energy, okay? And that is something tractable, and then that's something very, very like powerful. So originally, the way that like it was proposed is that, so at each time index, so this Hamiltonian systems, this h of t, it's a some time-dependent form, right? But collectively, when I integrate in a way, when I integrate out the all like time, the collective effect of this periodic derive, I'm doing it. So the system is described by this H-effective Floquet Hamiltonian. So like collectively, the physics that like I'm getting out of it can be something entirely different than this H of t, this time-dependent Hamiltonian that I start. And initially, this was proposed as a way to do Hamiltonian engineering. So there is something really cool physics that you want to see. For example, something called Haldane model. So Haldane got the Nobel for topology. And then there is this Haldane model. It shows that like to have something Chern number 1, you don't need to have a magnetic field. Okay, so there is some proposed model, but that model couldn't be realized experimentally because it's too complex. It requires complex next nearest neighbor tunnelings that cannot be done. That idea has been taken to optical lattices, cold atoms. If you start with some two-dimensional lattice, and then you start moving those mirrors that I was retrorefracting, okay? So if you move them slightly out of phase, when you move it, your standing wave position changes, right? If you just like move them slightly out of phase, this corresponds to taking this lattice and then shaking it circularly. And then there's a correspondence between the Lorentz force and then this Coriolis force that occurs. So you can create the magnetic field artificially in these systems. And then by using those techniques, because now this is periodic modulation, so that Haldane model has been observed experimentally in optical lattices for the first time, for example. So this has been first proposed Floquet as a way to do Hamiltonian engineering, the interesting Hamiltonian that you couldn't access by shining lights, just by shining lights on it, you can realize that physics. But then soon after, it has been realized that like, because now I don't have energy, now I have quasi-energy, and that quasi-energy is defined as the phase eigenvalues of that Hamiltonian. So it's a phase. So adding 2 pi to it is also a solution. So if I started with a 2-level system, I'm going to have, by adding 2 pi to it, I'm going to have infinitely many bands. So that's how the energy not being conserved translates into this picture, for example. And then there can be also band touching points between these Floquet replicas, which is a little bit artificial, but they can change the number of edge states. So the point is that before this physics, Chern number was saying that like it dictates the number of edge states, and then that is what controls your whole conductivity. But now here, your Chern number can be 0, but there can be still topologically protected edge states because of that additional gap. So the topological classifications we know, they had to be upgraded. And then the new invariants like winding numbers appear here, for example. So that is another thing, what's happening on the periodic deriving as some out of equilibrium correspondence. And then there is also, this is, so those topological singularities that you were asking there, so they can have topological charges. And then those topological charges, you can move them around and braid them. You can change their topological charges by braiding them. I'm just like really just like flashing at this stage. But what we can do, and then this is a physics that has been appearing in the last couple of years, taking these systems with this kind of topology, this is not Chern, this is something called Euler topology, and then by sending laser lights on it, for example, you can make those topological singularities move around and braid, and then they will go and then control observable signatures. So that is something interesting, and then I don't want to go into although this is my favorite, so let me tell you. So here, how many of you heard of the Bloch sphere that I was talking about? Oh, enough number of you heard about it. So this is like, Bloch sphere, when I have a 2-level system, so this is defined by something called SU2, there are the Pauli matrices generators of the algebra, there's the spin algebra that like I can plot them on the Bloch sphere. If you are looking at the time evolution, unitary evolution, this is like a spin precessing around the magnetic field, which is something you can imagine, okay? And this is the building block. This is a qubit, right? Spin, like all those quantum compilation applications. So this picture, Bloch sphere picture, is very useful, okay? So now, if you go to a 3-level system, there is something called a qubit 3-level system, or n-level system qubit. And then if I just like look at the Hamiltonian, this is a Hermitian matrix. Any Hermitian matrix can be fully written in terms of the Gell-Mann matrices, generators of the algebra. But now, for a 3-level system, I have 8 Gell-Mann matrices. So here, you were imagining 3 Pauli matrices, a 3-dimensional sphere. So now there, you need to imagine an 8-dimensional space and a 7th sphere. Sphere in the 8 dimensions is a 7th sphere. So the wave function is given by a vector on the sphere. And then the evolutions are, again, generalized rotations. And then if you have a 4-level system, a qubit, 4-level qubit, now you're in a larger spheres in 15 dimensions. Okay, so it becomes untractable again. And then you lose this nice visual intuition. So what we did here was that instead of trying to imagine a 7th sphere in 8 dimensions, you can imagine two spheres, which is much easier to imagine. And then the state is given by some vectors on each of these spheres here, okay? And then if you go to n-level systems, so there are n-1 spheres, and then each one is projected on. They're nested like the Russian dolls. And then the dynamics are given on them. And this is something we can analytically prove. And then, for example, for a 4-level qubit experimentally, to show that like they can create any 4-level qubit, they employed such structure, like 3 2-level sphere. So visual insight is important. So this is how I'm just like touching upon because topology comes from the geometry, and then the geometry of the Hilbert space is just like how this is appearing. And then outcomes of like these observables, that's how we are imagining and then connecting this physics to it. So that's what I'm just like showing you here. And then let me quickly just like thank my collaborators here. So I showed you, so several students worked on these things. So the ones that like I showed you their work, so I highlighted them there. So they were all undergraduate students here in Cambridge. And then I would advise you to seek projects, research experience. And then they all published their works here. With whatever you know, at whatever party you are on, just like taking it, applying it to a real research project, and then learning how this physics, like it can be slightly different. It can be a really fruitful thing. So my advice would be to just like seek out just like these research experience if you can, okay, during term or just like internships. And then several theory collaborators, particularly the works like that I shared you with Robert, Adrian, Nigel. They were all locally here. And then Misha and Walker, and then some of the experiments that like I showed you, mostly they were done in Germany here. And then also the cold atom labs here, there are really big cold atom labs also in the Cavendish, so getting some hands-on experience maybe. So I'm a theorist, I shouldn't be allowed near the experiments, but if you're just like working on quantum simulations, so you're really, I mean, as physicists, whatever we are doing, we're just like, it can be measured or just like that can be applied. And then knowing those techniques, like what can be done with lasers, just like new cool things, it allows us whatever physics, although no matter how abstract it is, by using what techniques I can imagine if I just like imagine lasers pointed along certain dimension, can I make the electrons tie those knots? So that's usually the last stage, and then also the fun part. So with that, let me thank you for your time. And yeah. Let me leave you with some cool pictures. Yeah.
Time to take several questions.
Oh, yes.
So, it was the same question I asked.
Okay.
So that we understand. How do you like studying this critical point, since it normally would kind of define a local order parameter. But the things they are highly non-local.
Yes, exactly. Yes. So whenever I have a singularity, so I have a singularity there. Okay, so that band touching point. So locally, the wave function is not defined, and then this topology is exactly the way that like the Chern number gives its effect is it's really non-local, because you need to look at the entire Brilliant zone to see whether it wraps the sphere or not. Okay, so what we can do that, although I cannot get the wave function exactly at that band touching point, I can get the, for example, Berry curvature, the wave function, right before or after. So the way that like you can think about this thing is that like that singularity there, I can close a sphere around it, some closed surface. I told you that like that's like a magnetic monopole, right? So there is some flux coming out of that sphere. And that's something I can calculate. Okay, that flux, if it's like a hedgehog or like if it's just like going out or in, so that is something quantized. So it's quantized by this, like its sign is sign of that band touching point. And then what we can do is that like so that is the sign of a Dirac cone, for example, band touching point. And look, if you can do a local tomography, get the wave function at all those points, that's something we can calculate, and then that can be also experimentally measured. It has been measured experimentally, but not by enclosing with a sphere in that sense. If this is really topologically protected, as I claim it to be, you can deform that surface, right? When there is a charge in it, the flux coming out of it should be independent of the shape of the surface. So I'm just like closing a sphere or a cube, it doesn't matter. It shouldn't matter, right? So that sphere, you can first make it to be a cube, okay? And then this singularity is sitting in the middle, and then I'm closing with a cube. So now let me deform that cube also a little bit. Let me make the top and bottom surface really large, and then the sides very thin. So it's like a slab, okay? Very large slab. So the flux coming out of that singularity sitting on top of it will be mostly given by the flux coming out of the top and bottom surfaces, for example, right? And that is something that Berry curvature on those bands, for example, around that. So since this is protected, it's like either +1 or -1 up to 4 pi or whatever units it's there, okay? So if I just like look at the flux coming out of the top and bottom surface of it, it will give me a sign. The sign of it gives the sign of that singularity. Okay, so but this is something highly non-local. So that's so anything topology is. So that's why like there's something called like local order parameter. So that's how before topology, that's how we used to classify things in physics, Ginsburg-Landau. But with this thing, so this goes beyond that. So I really need to look at the whole. I need to see the whole picture in that sense. And then for those singularities, like really as a very maybe too practical example. So that's how we treat them. So you can. There is some flux coming out of that magnetic monopole, and that can be measured. What's depends on what you're trying to do, because like what I showed you is a really just like small thing. Like for example, Chern number, it dictates Haldane model, for example. But there are certain things. For example, at the topological transition points, if you look at how certain things diverges, so you can just like apply similar ideas to it. Depends on a little bit just like, it's a really broad subject. So there are a lot of topological classes and different things. You can borrow ideas and then apply some there. So at topological transition points, certain things diverges, for example. And the way that like it diverges, it can tell you things, for example. Yeah. Which one? Oh, okay. Back one, this one? Yeah. Oh, it's not readable. So that guy is Schrödinger, and then the ball is a particle, and then the other one is a wave. And then it says, no one told me that I was going to have to work with her. Yes, that's the wave. I should have made it bigger. So yeah, that's the particle referring to a particle wave duality. Yeah. Yeah, exactly. Yeah. Okay.
What motivated you in moving into the field of quantum simulation?
What motivated me? That's yes. So I've always wanted to be a physicist, but as a kid, it just like started as just like, I admire stars, like it's universe is cool. You're just like looking up there. And then when I started the university, it just like happened to be quantum. And then I realized that quantum is actually really cool. And then with these kind of things, I believe that it's a little bit of luck that like you need to try. So that's also why I advise you to get experience if you can, because you don't have to like the first thing that you try. And then for me, I just like started working on this thing, and then I didn't start working on topology initially because like, I mean, as a physicist, you have a spectrum, right? So I also do superconductivity, localization, and other things. So I think it's important to get experience at whatever stage that you are at. And then why I like quantum simulations is that like, although I appreciate this math abstract side of it, and then I'm not coming from a math background, so I like that abstract things. But if I can just like think about a physical system, like bunch of electrons, as I said, like tying those knots, that's something pretty cool. And so that's why just like this requires taking those ideas and then applying to physical systems. And then why I like particularly quantum simulations or just like ultra cold atoms is that I think in cold atom theory, we are a little bit closer to experiments more than other branches, maybe. That because it's very also experiment driven, like these techniques like quantum gas microscopes, what optical lattices, what you can do, or just like I can propose experiments, go to experimentalists and then do that. So it's very just like intertwined in that sense, although I'm doing the peer-to-peer. So that's what I like. But if you're just like the one sentence example, like why you're doing this thing, I think it's luck. I could have been other things, yeah. No, no. I mean, of course, there could be corrections needed. You're just like when you're just like putting out a paper, you're just like making sure that it is there. And then if you're just like missing out any, I don't know, any point, no, that didn't happen. What they usually just like say is that like experiment is really dirty, right? So, and then as theory, we are just like assuming this is done. So we usually just like we need to meet in midway somehow that I need to, as a theorist, just like think about, just like throw away all the complications that I can to the systems. And then experimentalists need to amplify a few things and or just like come up with new ways to measure them. Yeah. Yeah. Okay. Thank you. Oh, yes.